fellow of many societies also, which are FNA Science, FNAE, FRSC, a globally recognized leader in electrochemical energy systems and hydrogen fuels technologies. Professor Basu is currently a FIPI chair professor in higher academic grade in the Department of Chemical Engineering at Indian Institute of Technology, Delhi, and had served as a director of the CSIR Institute of Minerals and Materials Technology, Bhubaneswar. He earned his PhD in chemical engineering from Indian Institute of Science, Bangalore, and has established an exceptional track record in research spanning fuel cells like PEM, AEM, SOFC, water electrolysis for hydrogen, CO2 reduction, and renewable energy materials. With more than 290 research publications, H-Index 56, multiple patents, and leadership roles in high impact projects, Professor Basu is a pioneer in linking advanced material science with industrially relevant hydrogen and fuel cell technologies. It is really an honor to have him as an expert for this FDP. I hope participants will gain so much experience or learning from Professor Basu. Professor Basu, you may please proceed with the presentation. Professor Basu, am I audible?
Can you hear me now?
Yeah, yes, Professor. You may proceed with your presentation.
Yes. So thank you, Professor Swami Naidu, for inviting me to give lecture on hydrogen energy in their FDP program. I'm just thank you for your nice introduction, and I'll just quickly share my slide. I just checked my slide and I shared it, and I'll just put my video off. I'll come back again just to have a better bandwidth for sharing the slide that I have. Just wait a minute, all the participants. If you have any question, let us keep the discussion at the end of the session. We have a long session. Just wait. I'm just sharing my window. I'm sure you are able to see my window. I'm just go to full screen now. Are you able to see my window? Anybody can just
Yes,
see.
yeah, yes, Professor, you may proceed.
Okay, so I will today I'll discuss this as a part of hydrogen generation, and we have reached to a certain stage of hydrogen energy or hydrogen technology that there is also a requirement of policy to take this technology forward, which quickly I will come into that one when we come to relevant discussion place. So what we are looking at is a closed hydrogen energy system that is promoted worldwide for the last 30 years, but we do not see the commercialization of this technology because primarily because it's not a primary fuel like coal, gas like methane or natural gas or petroleum, which is available naturally in the earth crust, and you have to mine it, and then many times you have to refine it and then use it. On the other hand, hydrogen is not available till now as any form which is in nature. So we have to make hydrogen. So for that you require energy. And of course, hydrogen can be made from fossil fuel like natural gas, methane reforming, or steam reforming of methane, even from gasoline as well, or naphtha, the crude petroleum. But the context, what for we are talking about hydrogen today is in the environmental context as well as energy context. Because all of you know that with the use of fossil fuel, there is a emission of greenhouse gases like methane, CO, CO2, and many others, which actually increasing the Earth's surface temperature as the heat generated on the Earth's surface is not able to released, or even if it released, not able to emit to the outer atmosphere or the space, because it is engulfed with all these greenhouse gases more and more, and then it is not emitting, and that's how the surface temperature is increasing, and that is how we are looking at a catastrophe, that when surface temperature further rises, ice cap will melt and many of our shoreline, not only in India or worldwide, will be underwater. And that's a big disaster for the earth. So that is why, from the environmental point of view, you would like to use a technology which doesn't emit, or you like to use energy where after combustion or any conversion, it doesn't emit CO2 or greenhouse gases. And hydrogen is one of the way of producing energy, where if you burn hydrogen, it doesn't produce any greenhouse gas the way the fossil fuel does. So there are two part. One part is the environmental aspect, that hydrogen gives a advantage. The other part, the energy aspect, that we are looking for a newer sources of energy. Now one day this fossil fuel will deplete completely, earth will not be available, and you also need to have an alternate source. But hydrogen is not available as an alternate source. Hydrogen is available only as an energy carrier. And if you're using photovoltaic, solar thermal, or wind energy, it is all intermittent in nature. And you want to give energy to your user continuously at the same level, then you produce more and more energy through photovoltaic or solar thermal or wind, and store it in the form of hydrogen by splitting water, and use it whenever there is a fluctuation energy generation by photovoltaic, non because of non availability of sun, or fluctuation of energy generated by wind when the wind is not blowing, or solar thermal when sun is not there. Then you compensate that energy requirement from stored energy in the form of hydrogen by splitting water. So that is how the hydrogen coming as a carrier of energy. In one hand, it is the energy source after the splitting of water and producing hydrogen. And on the other hand, when we use hydrogen to produce, there is somebody is having a side talk. Can you please switch off your make your mic, mute your mic. Please mute your mic. Yes.
Hello. Hello, Professor Basu.
Oh, how my mic was also muted because somebody was making sound. So from the in general they muted all the mics. So my mic also got muted. So do not worry. I'm again sharing the slide and I'm going to repeat what I said. Just wait.
Yeah.
Just wait.
Thank you, sir. Yeah, please, sir.
So can you see my slide?
Yes, sir. Please proceed, sir.
अच्छा इसका the format is little changed now. Are you going to see slides and other slides as well?
I'm going to see the slide number 2, sir.
And anything else?
No.
Okay, 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 fine. So let me uh, unshare and share it once more. It's the problem. Hmm. Stop sharing. Stop sharing. Okay. Why? Hmm. Oh, okay. This is better. Can you hear me?
Yes, sir.
Okay, good. So I was in this slide and somewhere in between it was stopped because there was some noise. So everybody was muted. I was also muted. So I'm continuing. So what happened is that um, I don't know where I left, but in a nutshell, that we are producing electricity by this methods of photovoltaic, solar photovoltaic, wind, and we are doing electrolysis. And from there, we are making hydrogen and oxygen. Hydrogen can be utilized in alternative petroleum chemistry. It can be used for cooking and heating purpose. Fuel cell can be utilized to produce electricity, and grid it goes, and it can be transported after liquefaction. You can use it in mobility by using fuel cell as shown you here. And the crux is that you have converted this intermittent energy into hydrogen and stored it and utilize it in fuel cell to produce electricity and burn it to produce heat or cooking gas, but you produce only water. So water, hydrogen and oxygen are burned to produce water. Hydrogen, oxygen is passed through fuel cell to produce electricity and produce water. So it is a closed hydrogen energy system where water is again reused again and again, and it is forming. And we are using the electricity or the energy of sun falling into photovoltaic, extracting the photon and producing electricity. Intermittent, because of intermittent nature, we are utilizing the power or electricity to electrolyze water to produce hydrogen. Same from solar thermal, solar photovoltaic, and wind. So that is why it's a closed loop system. And one is the production of hydrogen because it's naturally not available. Another is the utilization of hydrogen in a fuel cell to produce electricity. Third one is the burning of hydrogen as a heating value, heat value or heat market, or burning of hydrogen in oxygen in a burner to do cooking. In all time, water is produced, and so that is why it is closed to hydrogen energy system. Some more same thing is shown you here. That you have electrolysis, you have a hydrogen tank, you have a fuel cell, you have an inverter, you have a compressed air, whatever you want to, get electricity out of it, solar hydrogen system as shown you here. Okay, now I'm showing production of different production methods of hydrogen and different color scheme for hydrogen production as shown you here from left to right. Okay, so as I told you, currently hydrogen is prepared in different ways from fossil fuel, but our goal is to make hydrogen from from water using green source of energy, which is solar thermal, solar photovoltaic and wind. And so this is called green hydrogen. But currently hydrogen is used in refinery. Currently hydrogen is used for making ammonia or ammonium urea, okay, or ammonium sulfate, all being utilized as a fertilizer. Currently, hydrogen is used for hydrotreatment, hydrocracking in refinery, and all of this hydrogen is used by steam reforming of methane. So, based on the source of hydrogen, there is a color code, and these are not good hydrogen as we have been doing for last 100 years. That one is brown hydrogen when you take coal and you do coal gasification, okay, and you produce hydrogen, CO and CO2. During the coal gasification, steam is used and hydrogen is coming from there. So you produce syngas on CO2, and this is a brown hydrogen because this is a dirty hydrogen. A lot of CO2 and CO2 produced. So from the coal gasification. Next one is a gray hydrogen. The color code, which is universally given to everybody, is methane. After combustion, produce hydrogen and CO2, and again CO2 is produced, which is mostly not a combustion. This was gasification, this is reforming. It's called steam reforming of methane, and you produce CO2 and H2 and from natural gas. So this is a gray color hydrogen or ash color hydrogen, a gray hydrogen, brown hydrogen I talked about, gray hydrogen. And it is the same process. If you have carbon sequestration, the CO2 that comes out, if you can sequestrate, that means you can capture and store somewhere under the earth's surface, wherever, then it's called carbon sequestration. And if you do that, then the gray hydrogen become blue hydrogen. This is also not bad because although you are using fossil fuel, let's say natural gas, but you're producing hydrogen, and CO2 you are capturing and storing it, not allowing go to the atmosphere. As I said, the greenhouse gas in atmosphere is really big problem. Best is to produce hydrogen from water, and it is called green hydrogen. So anything that you use without fossil fuel is called green. So you take windmill or photovoltaic, use the electricity, do electrolysis of water to produce hydrogen, oxygen, and that hydrogen is called green hydrogen. But the cost of this green hydrogen, because you require electricity, is much higher than the cost of hydrogen coming out from coal or natural gas. And combination of these processes gives rise to many other color, like you have a gray and brown I talked about, you have a turquoise here, you have a purple, you have a pink, you have red and white. So green, blue, gray and brown I have talked about. Then you have a combination of processes where you get other color scheme. And the last one is white hydrogen. White hydrogen, people are predicting, but not so far actually proven. Only they have predicted that somewhere in Africa and in USA, they under the shell, underneath the surface of Earth, and it is the hydrogen naturally is occurring, and that is true, then that hydrogen will be called white hydrogen. But we do not know, it is all prediction. So this is what the hydrogen is. And then traditionally, different way of making hydrogen is hydrocarbon reforming or gasification, like steam reforming of naphtha, steam reforming of methane, partial oxidation, autothermal reforming, biomass gasification. Okay, these are the hydrocarbon reforming process. Okay, that then we have PEM water electrolysis. PEM, I will talk about what is PEM, proton exchange membrane, but this is an electrolysis process. So electrolysis is what is green, and where hydrogen water with electricity produce hydrogen and oxygen, and efficiency is 50 to 70%. Photocatalytic water splitting, that means you have TiO2 photocatalyst, it takes photon, then it actually have holes and
Professor Basu, you have muted your mic.
so it was got muted.
Okay, now we can hear you.
I know I am not muting it. Who is muting? If you are
Not.
doing, if you are muting it centrally, then everybody's mic, then my mic also will get muted.
No, we haven't done it. Is so another person also can unmute it now. We haven't muted it. Sorry.
But who muted?
I'm not sure, sir.
So anyway, so shall I continue? From
Yeah,
where
yeah.
you are not able, you have to immediately tell me that you are not able to hear me. Then I'll react. Otherwise, I
Yeah,
have to
just
go on
now.
repeating.
Just now, sir. Just now, sir. That's why we have updated you.
Okay, okay. You please tell me if it happens again so that I don't have to repeat
Yeah,
it.
yeah, yeah. Please, Professor. Please continue.
Okay, okay. Because when I'm going to the full screen, okay, now I will be able to see it. I better see that I'm not muted. Okay. I have to take the, okay. Okay, so then thermochemical route, hydrogen, heat plus H2O, and then thermochemical with a catalyst, you can have water splitting as well, like SI cycle, sulfur iodine cycle. But these are the process of making hydrogen. So first steam reforming of hydrocarbon is having a byproduct of CO2. Biomass also will produce CO2, but biomass source is renewable because as long as earth and sun is there, biomass will be generated. Electrolysis of water is completely green process, as I told you. Photolysis is like photochemical, photoelectrochemical. Photon is captured by semiconductor catalyst, and then with the holes and electrons, it produces hydrogen oxygen after reacting with water. And then these are thermochemical process. And what we are looking at in the in coming time is only to have talk about the green hydrogen, because other processes are well developed. As I told you, that in these processes like shown you here, that you take coal, you have a gasifier, you have shift reaction, then gas cleanup, then you produce pure hydrogen, and you need to then store CO2, sequester it, and then you can tell this as a blue hydrogen. And so this is a gasification. You can take natural gas for partial oxidation, or you have a reforming, steam reforming of methane, autothermal reforming process. All places CO2 is produced along with hydrogen, and you need to clean it, and then you can have a blue hydrogen. And the processes are shown you here. So I am not going to delve much on it, because all of you know this part. And our current talk is not about the hydrogen that is coming out of fossil fuel, because it co-generates or it generates byproduct, which is CO2. Correct. So that's what we don't want. We want a process where it is completely green. Okay, so uh, uh, before going to the technologies of hydrogen production from water, green hydrogen production, let us see in 2021 and it is 2025. So there is slight change in the production or the requirement of hydrogen. This hydrogen requirement is mostly in refinery, in ammonia plant, and so. And you can see India's requirement is currently, it's slightly changed, slightly increased, 7.4 million tons per year of hydrogen. And United States is about 11.3, and China is the highest, about 29, 3.9. And all these are utilized in refinery because of hydro treatment, in ammonia or ammonium sulfate or urea making, because you need to produce fertilizer. So that's the bulk of it. But because of the so much of talk going on, so much of pledges has been taken. By 2050, India said by 2070 we will decarbonize, means the carbon footprint will not increase but maintain. That means we will not emit more and more carbon dioxide. It will be maintained in the level which was there maybe 10 years back, 20 years back. And that if it's maintained, then the Earth's surface temperature will not rise and we will be safe. So everybody is taking pledge, and hydrogen demand would increase and green hydrogen demand would increase. So what we are looking at, that today the total hydrogen requirement is, let's say, about 94, 95 million tons per year. And it is projected, because everybody takes a vow that I'm going to now decarbonize. I'm going to use more and more green hydrogen for reduction purpose. For ammonia making, the bulk, the fertilizer, I will use green hydrogen. For steel making, I'll use green hydrogen to make steel, because you require a reductant, and the reductant is coal and coke. In the case of steel making in blast furnace, you can use hydrogen for reduction. In refining, you need to do hydro treatment, because hydrogen is added for octane number, cetane number maintained. So that is how we will use green hydrogen for green refining. And it is projected that everybody had uh, agreed that by 2050 we will decarbonize, India by 2070. So hydrogen requirement will jump from, let's say, about 94.3 million tons per year in 2021 to 180 million tons per year in 2030. I mean, it is more by 2050, because everybody is using green hydrogen, not the fossil fuel hydrogen. And so projection from 2050 is for India is shown you here. It is going to be almost India by 2050 about 30 million tons of hydrogen, okay, per year. Okay, currently it is about 13, 14, 20 by 2030 it will be about 13, 14 million tons per year. Currently it is 7.2 or 7.4 million tons per year, as I was showing you in the previous slide. 7.2 maybe in 2021, today it may be 7.4 million tons per year. Okay, so what we are showing, the hydrogen demand by 2050 is going to rise like anything for India, and it's going to be close to about 27, 28 million tons. Today it is 7.2, almost 4 times than what we are today. And how we are going to use it? You can see here that ammonia fossil fuel oriented, methanol fossil fuel, refining fossil fuel is going to be ammonia green, refining green, methanol green, steel green, transport also. So all these areas are industrial use, not for transport, very less. In 2050, majority will be industry using green hydrogen, which is the green part, and the gray hydrogen is reducing. Okay, different types of gray shades for different type of hydrogen. In the case of methanol, ammonia, fossil is all going to decrease, peaking at 2030, then it will decrease. But the green hydrogen is going use is going to increase. Okay, that is what we have shown you here. That's what it is. And mostly in industry, little bit in transport and little bit in power. So this will happen. There's a lot of big investment is required. Okay. And already government is investing last 2-3 years. They have earmarked about 2,000 crores of investment just to, pilot plant setup and R&D. In R&D, they have kept about 400 crore, and out of rest of the 2,000 crore that I talked about, remaining 1,600 crore is for Hydrogen Valley and Hydrogen Hub program. That's why the policy is important. So if government supports, then obviously it will be very good. It's a good thing to do, right? That's what we want. If the government support is there. So there will be big investment is already taking place. And this is only from the government side, but the industry also have to, invest. So all the companies, those who are in the photovoltaic and then wind power, even refinery, steel, they're also investing in green hydrogen making. Okay. So steps taken by government is green hydrogen policy, which has come up, green hydrogen mission uh, of India has come up. Okay. And then electric vehicle policy has come up, because these are transitioning to use of hydrogen, right? Electric vehicle, preparing people mind that no more emission electric. Of course, electric, if the charging is done through photovoltaic manner, then it is truly green. But if charging is done by thermal power plant based on coal, then it is truly not, it is truly not a green process. But we hope slowly that we will be charging our electric vehicle using photovoltaic, using green power coming from windmill and so on and so forth. Then government have announced production link incentives. That means if you produce green hydrogen, then, or if you produce green hydrogen and electrolyzer for green hydrogen, and then you will be given some tax benefit, your cost associated with a production will be compensated by the government depending on what you subscribe. So recently all big companies subscribed PLI scheme from 300 megawatt to 30 megawatt, as low as 30 megawatt. Some of the smaller company, 300 megawatt, larger big companies said that they're going to put the electrolyzer, because many of these companies actually hold a photovoltaic park. So PLI scheme is being announced. And then other things is going to come, which I'm not going to discuss much because this is on all policy, right? So let us move forward. Here I'm showing that how we are going to, see that from 7.2 million in 2021, maybe 7.4 or 5 today at 2025, to going to about 12 to 13 million tons per year by 2030. Okay, and 28 million tons of hydrogen by 2050. This is the demand in India alone. And there will be demand also in the world. So if India having very good sunshine almost throughout the year and throughout India, using photovoltaic, also wind power, the green hydrogen production scope is much higher in India. Having coastline, having so many ports in the coastal area, if you produce hydrogen because of the photovoltaic park, and then immediately shipping through port to other countries like Europe or Japan, it will be very good business proposal. And that's what is happening. So based on these policies like Acme Solar, Adani Group, Amp Energy, Avada, Azure, Greenco, JSW Energy, NTPC, Reliance, Renew Power, Tata Power, Torrent, everybody positioned themselves of different value chain of hydrogen production, electricity generation through photovoltaic or wind power, and then use that electricity to split water or electrolysis of water to make hydrogen, store it, so energy storage, and then supply of hydrogen of different places, exporting it to other countries is how these companies have come. So why I said that I'm also going to discuss policy, because this is such a technology. If the government doesn't support, because the cost is high, that is how even so many countries, the developed countries like USA, Canada, Germany, France, Japan, working for this technology for last 30, 40 years, but still it is not commercialized because of the cost of hydrogen, which is about, let's say, if it is your gasoline price is about 90, 95 rupees per liter, or your Indoprastha Gas Limited or your natural gas cost per kg is about 70 or 64 rupees. The hydrogen cost is 1200 rupees per kg. Is 10 times or even 12, 14 times of the current rate of natural gas. So who will use it? No one will use it. So we required a support. We required technology development to reduce the cost, and then we required a support or encouragement from the government. So that's why the policy is important. Otherwise, naturally, you would have seen that hydrogen is coming and taking over every sources of energy that we talk about. But this is not going to happen because the cost is very, very high. So that's how the policy is important. And I wanted to, discuss this. So this is a cost. So cost I have already talked about. Now let us come to the technology that we wanted to discuss, right? So yeah, I'm only talk about the electrolyzer or electrolysis technology, which people thought to be a very fast responding technology, in the sense that you can produce hydrogen in lot amount in quickly, and you can regulate the production. Whereas if you talk about photocatalytic, the process is very slow. If you talk about microbial, electrolyzer or microbial technique, also the rate of generation of hydrogen is low. So this is a very good responding technology for hydrogen generation from splitting water or electrolysis of water. Okay, so there are two ways the water can be split in the presence of alkali and acid, right? So yeah, I'm showing you the reaction. This is an electrolysis. I'm sure all of you have a idea about what is electrolysis. You have an anode and you have a cathode, which is known as electrodes, and then you apply potential difference between the electrodes. Then it undergoes electrolysis of water, as shown you here. In the case of alkaline electrolyte, when KOH or NaOH is used as an electrolyte, then water will take two electron because you apply potential difference, produce hydrogen and hydroxyl ion. The hydroxyl ion from cathode will move to anode, and it will undergo an oxygen evolution reaction, OER, and hydrogen evolution reaction, HER, as I mentioned here. So the hydroxyl ion will be transferred from a cathode compartment to the anode compartment, where it will split into oxygen, H2 and 2 electron, and these 2 electron from the outer circuit again will reach to cathode, and the process continues. So this is an alkaline electrolyte electrolyzer. Same way I can have an acid electrolyte like H2SO4. Then it is slightly different reaction scheme. H2O splits into oxygen, proton and electron. Electron from outer circuit comes back to cathode, and proton moves from anode to cathode. The proton electron are added and produce hydrogen, and this is what it is, the acid electrolyte through which you have the electrolysis of water. Okay. Now this is kind of a, when you're using a, liquid acid and liquid KOH, that means alkaline solution and acid solution as electrolyte. But that is not good because it can spill, it is not stable. So people have developed solid electrolyte like membrane electrode assembly made of proton exchange membrane. Solid electrolyte is what people use it today rather than liquid electrolyte, because liquid electrolyte spilling problem, containing problem, and all those issues are there. Okay. So how a alkaline water electrolysis cell works? Cathode anode reactions are shown you here. Anybody is having any question? You can raise your hand, or maybe we will do at the end, not now. Okay. So alkaline water electrolysis is schematic diagram is shown you here. At the cathode, again I am repeating, this was shown you before, that it takes water and two electrons, produce hydrogen and hydroxyl ion. Hydroxyl ion move internally through cathode to anode. That means from cathode to anode, hydroxyl ion moves. It gives up oxygen, it gives up H2O and two electron. So this electron is being released, which is moving through the potential difference that is working towards the cathode again, an electron plus water to produce hydrogen and hydroxyl ion, as before we have talked about. So this process is going on here. Let us see the scale, the elements involved in the alkaline electrolyzer. So you have a diaphragm to separate the anode and cathode, because they should not touch, otherwise it will short. So electron will move through this, not through the outer circuit. So a diaphragm is kept in between anode and cathode, and you are fed in the first reaction, you are fed with hydroxyl ion or water, like this reaction. So you are fed with water, and it takes two electron, hydrogen and hydroxyl ion. This hydroxyl ion moves here to the anode. So hydroxyl ion comes to the anode, then it splits into oxygen, water, and electron, which is what shown you here, right? So essentially, electrolyzer contain an anode and cathode electrode, which is like electrocatalyst, help the reaction to take place. Then in between, you have a diaphragm through which hydroxyl ion moves, and also it doesn't allow the electrons to come from anode to cathode or cathode to anode, because this is a dielectric, not a conductor of electrons. So that's how what is important. On the other side, there is a availability of water, and because of the potential difference applied between anode and cathode, it undergoes this reaction as shown you here. In a way, it produces oxygen and hydrogen, and that is what is shown alkaline electrolyzer is. So just wanted to show that this is not enough, right? And only producing electrolyzer will not help. So electrolyzer or electrolysis process produce hydrogen, oxygen, and your delivery point is here, where hydrogen should be available at certain pressure so that it can fill another tank and certain purity. So that is important, right? So this is called balance of the plant, or the total typical system or balance of the plant. Okay. So electrolyzer is here, only small. Rest is required, to actually have the system. Without this system, we call it balance of plant. There's a balance of plant also in thermal power plant. So that is also there, except for, generator. Everything else is balance of the plant. So that is important. And it also almost like 50-50 cost sharing. So whole system, if it is 100 rupees, the electrolyzer cost will be 45 and the rest of the thing will cost around 55. This is roughly I'm talking about, depending on the design, depending on the size, depending on technology and things like that. But roughly, even it is like this. So let us explain this. You have feed water. You need to purify the feed water. So you're going through a simple separator or filter. Then it goes to uh, it meets the stream where the alkaline medium is there. Okay, and then it goes to the electrolyzer. So it's a water source for electrolyzer, and blue is the electrolyte, which is KOH NOH along with hydrogen oxygen is coming up. There is a disengagement of electrolyte from the cathode side, anode side, hydrogen oxygen, which goes as a gas, and the unreacted water having more hydroxyl because it is alkaline electrolyzer, goes down, makeup water is added, makeup NOH, KOH, if they are the electrolyte added, okay, water KOH electrolyte tank being added, measured, and they are all the, whether they are in the right temperature, pressure, okay, and they are being sent to electrolyzer again. Here at the bottom is also very important. Sending a giving voltage minimum, but required voltage. You get the high voltage from the power supply, like in a high voltage power line. If it's not photovoltaic, then you have to have transformer and rectifier, because this is an AC supply, and this is what you require is a DC. So AC to be converted to DC by transformer rectifier, and you have to have a very good voltage, constant voltage range, no fluctuation, so that all the time electricity takes place at the same rate, and water and unreacted water, hydrogen oxygen is generated, they're disengaged in this channel, and oxygen goes and vented, and hydrogen, moist hydrogen, I would say moist hydrogen, is going to the next step of gas water separator, okay, then dryer, and further you can store it, you compress it, the compressor sign is there, to a high pressure tank, and then you sign it, or high pressure tank, and then it, you have to dispense it, right? Not sign it, it's dispense it. So you have to dispense hydrogen. Okay, that's the whole process or system that you require. Okay, so now I have given only alkaline electrolyzer. Same way I can talk about PEM or acid electrolyzer or solid oxide electrolyzer. Okay, same way. So diagram I'm not showing right now. So what I'm showing you here, the difference between alkaline electrolyzer, acid or PEM electrolyzer, and solid oxide electrolyzer. You can see the charge carrier is different, OH minus, H plus, O2 minus. Reactant water, of course, electrolyte is sodium potassium hydroxide, polymer membrane, ceramic. And then you have something like electrode, nickel metal oxide, nickel ceramic, and etc. Anode reaction, I already showed the reaction for alkaline, and for acid also I showed the reaction. Water splits into oxygen and proton. Proton moves from anode to cathode, takes 2 electron, produce hydrogen. And the temperature ranges are mentioned here. This is for solid ceramic. Solid ceramic membrane is used, nickel as electrodes, LSM or lanthanum strontium manganate is used as electrode, and it operates at a very high temperature. So it has got a long startup time, shutdown time is also long, high temperature requirement operation, not so easy, 800 900 degrees Celsius. This is you relatively lower temperature, 600 to 170 degrees Celsius. Steam, maybe when you do steam electrolysis, high energy density, compact design, and medium temperature operation. Okay, 60 to 170 degrees Celsius. And this is 80 degrees Celsius alkaline electrolyzer, circulating electrolyte. And so this is we circulate because the electrolyte is circulated, which we talked about in the electrolyte is circulated, right? The blue color, the light blue color. Okay. So this is what we have a difference between alkaline acid and solid oxide electrolyzer. Now I'll talk about photocatalytic and photoelectrochemical water splitting or photocatalytic process, which I have been talking about. Okay. Let me have a break of 5 minutes. Can we have a bio break of 5 minutes? About 1 hour that we have spent. I will also speak about another half an hour, 40 minutes. So can we take a bio break? All of you agree? All the participants? Just 2 minutes?
Yes, Director.
Yes, sir.
Okay, sir.
Okay,
Please,
very
sir.
good. Be on the line, don't go away.
Yes, sir.
Yes, I'm back. So all of you are here. Let me continue. So here I am showing you the uh, okay. Here I am showing you the photocatalytic photoelectrochemical water splitting. So you can take a photocatalyst, mostly semiconductor catalyst, and it's shown you here schematically that this takes a photon, the semiconductor, and it's then with the help of photon, it generates electrons and holes, and usually they recombine and nothing happens. But if you design a photocatalyst such a way that you don't allow electron and hole to combine or recombine, then they remain and they're very active because they are not stable. So electron would like to react. So it reacts with water to produce hydrogen, and holes react with water to produce oxygen. But the problem of this method is here that hydrogen, oxygen both are generated at the same time and they're not separated. So what you get gas is both hydrogen and oxygen together. Okay, so this hydrogen oxygen need to be separated to produce by membrane separation technique or any other technique, adsorption technique, to separate hydrogen and oxygen. That's the disadvantage of this process. But if I use a photoelectrochemical cell, having one side semiconductor using a photoanode or a photocathode, another side is normal cathode, in this case photoanode and normal cathode, then it takes the hole and then produce proton and oxygen, and there is a membrane in between through which proton moves and comes here, takes electron, produce hydrogen. So half of the electrode is, semiconductor, which is photoactive. Other half of the cell, which is normal electrocatalyst or electrode, which can be platinum, let's say. And then it has got two compartments separated by naphion or proton exchange membrane, which allows only proton to transfer. And hydrogen and oxygen are generated two separate compartments, they don't mix. So compared to normal electrolysis cell, since we are using photon, this takes little less energy to split water compared to the complete electrolysis process, because part of the energy is coming from photon, which is sunlight, which is free to you, it's falling onto it, something like that. And here I'm shown that if you have properly designed, like I have shown you here, bismuth vanadate, BiVO4, and tungsten oxide, and nickel iron chromium layer double hydroxide in such a way that holes and electrons never recombine. They are separated. One is taken away by nickel iron chromium layer double hydroxide. Another is taken by tungsten oxide, the electrons. And then this reaction takes place. No recombination. Platinum as the cathode, where hydrogen is generated, here oxygen is generated. So this is a kind of heterojunction photoanode. You design such a way this recombination of proton or electrons and holes doesn't take place. Okay. So this is a photocatalytic or photoelectrochemical water splitting. I'm not going to discuss much on this, but list of hydrogen making, we showed a few processes from water gas shift reaction or gasification or reforming from fossil fuel. Then we showed the green hydrogen from water splitting or electrolysis of water, and the photolysis or photocatalysis and photoelectrochemical process. That is how I'm showing this, so that I complete this part. Now I made hydrogen, and how I can now use hydrogen. One of the way to use to simple burn, in if you using for calorific value for cooking or making heat for heating a room, cold countries, in our case maybe in the Himalayan area, but not otherwise. We do not have heating problem except for a few places in the north, but mostly we are all climate is all the time is hot. And so here I'm showing how fuel cell works. It's almost similar to electrolyzer, just in the opposite direction. So you have again three compartments like electrode separated by membrane of electrolyte, and hydrogen is supplied to the anode, platinum, It splits into proton and electron. Electron goes from the outer circuit, which is the electrical energy it produces, and it comes back to the cathode. Proton, on the other hand, moves from 3 to 5 through 4. 4 is a membrane or electrolyte, proton exchange membrane, allows only proton to move, and it is a non-conductor. So there is no shorting of anode and cathode. And then it is proton, which is moving from 3 to 5 through 4, combined with oxygen coming from air and electron coming from outer circuit to produce water. And this is a net process of hydrogen, oxygen giving water. In the process, electricity is generated because electron moves from 3 to 5 from the outer circuits, and that itself is a passing of electron through a wire, and you say the electron is generated. Now, this is a schematic, but more elaborate drawing of how a electrolyzer, or in this case, fuel cell, would look like. So you have a membrane electrode assembly, MEA. Membrane is the electrolyte, that 4. Both sides of membrane will be electrode 3 and 5, which is shown you here, and together they call membrane electrode assembly. Then you have a gasket. Then you have gas diffusion layer for supplying of gases or distribution of gases evenly throughout the electrode. Then you have one more gasket, okay, and then you have a bipolar plate. Here it is almost like a monopolar plate because there's only one cell, and this is made of carbon or graphite, and there is a channel through which water, in the case of electrolysis, or hydrogen in the case of fuel cell, moves around, and it opens to this gas diffusion layer through that anode side, and here the cathode side, and that's what it does. Okay, so I've shown you here, it is an efficient way of conversion of chemical energy into electrical energy by using fuel cell. It is environmental friendly, hydrogen, oxygen giving water, no carbon. It can generate electricity, can run an automobile, it can power a house or a villa or a city, part of city, and it can also power a portable electronic equipment. That's the advantage. Like it is being blown up or magnified, the whole membrane electrode assembly, the sub gasket, the graphite plate, or the fuel distributor, as shown you here, right? This is membrane electrode assembly. This is a gasket, sub gasket, gas diffusion layer. Then this is a graphite plate through which this serpentine flow filled, the gas moves and get exposed to the anode. Oxygen comes or air comes, get exposed to the cathode, and those reaction takes place. Now about the electrolyte, and I've been telling this is a polymer electrolyte. It is a proton exchange membrane electrolyte. So I'm talking about this like a membrane because it allows only proton to move. So it's like a membrane. Polymer electrolyte membrane, proton exchange membrane, whatever you say, it's like a PEM in short. And this is what is like a polyethylene as shown you here. This is how a DuPont polymer electrolyte membrane or proton exchange membrane or PEM would look like. It's like a polymer sheet, and it's generally wet when you are utilizing it, and it allows proton transfer to take place through this. Nothing else can be transferred. Moisture transferred or water transferred, because proton requires water for transportation. That is allowed, or that is how it is designed. Nothing else, no other ions are allowed. Now, what is the design? Why it behaves it is such a way? Is it has got a PTFE backbone. Okay, CF2 shown you here, which give the strength to the membrane. Side chain of PTFE, polytetrafluoroethylene, having oxygen, CF2 and SO3 minus. Small minus can be seen. If it is not visible, just see that SO3 minus. This side also O, CF2, SO3 minus. So like that, this white color is a white space. so small that you will not be able to see here. And the gray color is the PTFE, polytetrafluoroethylene, gives the strength to the membrane, and white space where the bond is dangling, a dangling bond, it is kind of um, uh, you can say um, like a swing, dangling bond. Okay, and this is a white space. This white space is usually soaked in water. This membrane and white space is occupied by water, and H3O plus, the hydronium ion, through which one SO3 group to another SO3 group to another SO3 group, how the proton transfer takes place. Because there is a difference in concentration of proton, which is generated in one place, used up another place. There is also a potential difference between anode and cathode, and in between is the electrolyte or the membrane. So because there is a potential difference, okay, so there is a, proton transfer takes place from anode to cathode, under the potential concentration difference, and which gives the diffusion, and the potential difference which gives the migration. So that is membrane, and on the membrane through CCM technology, catalyst coated membrane, the catalyst is coated, this anode and cathode. So this is called the MEA, membrane electrode assembly. Okay, that's the heart of the cell. Okay, MEA, membrane electrode assembly. Usually the fuel cell operates at 70 degrees Celsius at 1 bar, that means atmospheric pressure. So that is how I will generate. I will uh, generate hydrogen in electrolysis, then use fuel cell to produce electricity whenever is required. Okay, so in the case of fuel cell, again you have a balance of plant, because it's similar to electrolyzer, but in the opposite direction it's working. When you are generating hydrogen, it's like charging of a battery. So you are generating hydrogen. And when you are discharging, then you are using this hydrogen fuel cell to generate electricity, like charge discharge battery. So charging is like hydrogen generation is the electrolyzer, and discharging is utilizing hydrogen in fuel cell and produce electricity. It's similar, right? So we are showing you the balance of the plant. So you have a fuel cell stack. So what we don't use one single fuel cell, because one single cell will only give you 1 volt. Okay. So, but I required some 220 volt. So I required that many cells. Maybe I required 60 volt if I run a simple, let's say 2-wheeler. Okay. So then I required that many cells. So that is how the stack. So stack is generated, correct? Fuel cell stack, then there are managers, air, thermal, water sensors, that what rate air is coming in, thermal change in the heat dissipation or heat exchange, water control, and sensors. So hydrogen storage area through membrane humidifier, because it should not become dry, hydrogen goes into the anode side. Okay, and how humidification takes place, because the water that is forming, which is having moisture, can supply or humid the hydrogen that is already stored after generation of hydrogen. And then we have a demister shown you here. Enthalpy will take out water, enthalpy will take out your heat. Okay, and then you release that unwanted water vapor if it is not required. And warm humid inlet air is of course be given there, which is coming from this side. Cool dry inlet air, and with the enthalpy wheel you try to exchange and heat it to the operating temperature, so that the air side or the cathode side air is also working at 70 degrees Celsius. No temperature gradient. Okay. So except for fuel cell, whatever else you are seeing here is called balance of the plant. Okay. So we are all working in these areas at IT Delhi. We are working on micro electrolyzer developed at TRL4. We have a startup. We have electrocatalyst for non-PGM alkaline electrolyzer and PEM electrolyzer, means non-platinum group of metal like phosphonates. We do a lot of modeling. We have fuel cell development, fuel cell poisoning, a direct hydrocarbon PEM fuel cell we have developed, solid oxide fuel cell we are working on. We are working on lithium, sodium ion batteries, spent battery recycling, and electrocatalyst development. So I would like to stop here because because 1.5 hours of interaction. So it is about 9:15 or 9:16 now. I guess we are up to 9:30 or 9:35. Let's say we started 5 minutes late. So can we have a question answer session now? Because that will be more important for FDP program if somebody is having any question. Can we do that? I can stop sharing, then we can have a question answer session. Anybody is having any question? I'm not hearing from anybody. Anybody is having any question? I know it is quite late. Can you hear me?
Yes, sir. Yes, sir. Participants, is there any query? Any doubts or any clarification?
Any doubt or anybody is having any question? Because I can go on speaking. Anybody is having any question? Professor Naidu or Dr. Naidu?
Yes, sir.
Shall I continue or do some more? What is if there is any question by anybody, or if you have any question, you can also ask me.
Yes, sir. From the participants. Participants, any question?
Who is that? You can raise your hand and ask question, or you can simply speak. I think they are allowed to speak. They are muted, or you can allow them to talk.
Yes, sir.
Sir, good evening, sir.
Yeah.
Sir, good evening, sir.
Yes.
Sir, in fuel cell, what is MEA application, sir? What is the use of MEA?
Okay, Dr. Praveen Kumar. So MEA is membrane electrode assembly, correct? So membrane electrode assembly is the heart of the fuel cell. Even fuel cell and electrolyzer operates exactly same way, but in terms of the what it consists of. But in the case of electrolysis, you apply potential, water splits into hydrogen oxygen. In the case of fuel cell, hydrogen oxygen combine to form water and you get electricity. So it is kind of opposite. Now, the membrane electrode assembly, if it's a PEM electrolyzer or PEM fuel cell, proton exchange membrane fuel cell or proton exchange membrane electrolyzer, the role of membrane or role of MEA is same. That means it has got a electrolyte membrane which is DuPont proton exchange membrane, which allows proton to transfer, which I was trying to tell you towards the end when I share my slides. I'm sharing again because if that is a question, I'm just loading my slide. Reduce my bandwidth. It is not allowing, is it? Let me see. PowerPoint Live, preparing your slide. Correct. So let me go to the relevant slide. I was in this slide that I was. So this is the slide. So you can see that this is called MEA, membrane electrode assembly. So we have the electrolyte, which is of this nature, which is polymer membrane. Okay. And then it is gone now again. It is automatically not allowing me to share. I don't know why, but let me see where it is. Okay, here. So it is this MEA is membrane electrode assembly, and you have anode, cathode, and PEM. And the PEM is this, and that is the heart of the fuel cell or heart of the electrolyzer. Any more question?
Okay, sir. In starting, you explained the applications of the hydrogen gas and all this, sir.
Yeah.
What are the brief applications, practical applications? Can you please explain, sir, again?
Yeah, I think I was talking about application is like I said, I'm not going to slide again because there's some disturbance looks like. So it is main application of hydrogen industry now is three. Immediately, because of no one wants greenhouse gas emission or want to stop the CO2 emission or carbon emission, you need to produce a lot of fertilizer for your agriculture. Everybody, all countries, Africa, India, Asia, Africa, Europe, North America, South America, everybody, Australia, everybody required agriculture. That is the mainstay of the human civilization. And because the population is increasing, so you require a lot of fertilizer so that we have a good growth of your all the agricultural product. And ammonia, urea is the main fertilizer, right? NH3 or NH4, SO4 or urea. Okay. And so you have a nitrogen, hydrogen in that, and that nitrogen is coming from the atmospheric air, and hydrogen is coming from fossil fuel, which is steam reforming of naphtha or steam reforming of methane, and you have CO2 emission. So first utilization is, as everybody is saying, that we want to decarbonize to make green ammonia. So your hydrogen that is required for making ammonia should be green hydrogen, and that ammonia should be called green ammonia, and that is government should promote that. And already many other countries promoting it, that let us use green ammonia, not normal ammonia, which is utilizes a lot of coal coke for generation of hydrogen, which then through Haber-Bosch process, nitrogen, hydrogen at high pressure, high temperature produces ammonia. Some 200 bar and about close to 370 degrees Celsius. Okay, if you remember, that's the process of Haber-Bosch process. People say now use green hydrogen, so green ammonia. Next is the refinery. Your petroleum refinery does a lot of hydro treatment and hydro cracking. So they use hydrogen, to infuse inside the carbon molecule so that your C10 number is improved. You don't have anti-knocking agent. So you require hydrogen. That hydrogen also comes from the fossil fuel, naphtha reforming, natural gas reforming. So that hydrogen should be also green hydrogen. Then we say that is a green refining. Okay. Next one is the highest emitter of CO2 is one of the highest emitter of CO2 is the steel industry. Steel is Fe2O3, which is known hematite ore, Fe2O3 or Fe3O4, and they have to reduce Fe3O4 or Fe2O3 to Fe, and they use coke for reductant. Okay, they use coke for reductant, and instead of coke, you can use hydrogen as a reductant to take away your oxygen from iron oxide to make iron, and then it could be called green steel. So these are the three places, big weight, the big emitter of CO2 and big use of hydrogen is green steel, green ammonia, and green refining, green methanol, green ethanol, and all those things. Okay. So that's the industrial use. I'm not looking at fuel cell use and mobility and electricity generation at this time. Okay. Any
Yes,
more
sir. Thank you
questions?
very much. Thank you very much,
Yes.
sir. Thank
Okay. Thank you.
Hello, sir.
Yes.
Sir, can you please explain about the startup time, how it varies for different electrolyzers and why?
Dr. Arun, what is your question? Different electrolyzer, what you said?
Startup time, sir.
Yes,
When
yes,
integrate.
yes. Very good point. Very good point. So primarily we have three type of electrolyzer at this time, which is popular and commercialization is happening. Most popular and cheap electrolyzer is alkaline electrolyzer. Now, alkaline electrolyzer can work on anion exchange membrane, but hydroxyl ion transport membrane, but that is not well developed. That's not popular. That's not robust. That's not stable. So it is liquid alkaline. That means alkaline solution or aqueous alkaline, water with alkaline KOH or NOH is used as electrolyte. Okay. And this operates usually operates below 100 degrees Celsius, but one can also utilize slightly high at 140, 150 degrees Celsius as well. Okay, so, and that atmospheric pressure is about 1.52 atmospheric pressure or 5 atmospheric pressure. So to maintain this starting of this electrolysis process is simple, not much time. PEM electrolyzer operates about proton exchange membrane electrolyzer operates about 70-80 degrees Celsius at maybe 235 bar or maybe 10 bar. So here also temperature is not very high. So you can generate pressure generates generally when you produce hydrogen oxygen pressure generates. So here also the startup time is not so. So these have very quick startup time in a minute or in a 2-3 minute alkaline and PEM electrolyzer will start. Alkaline may be little if it's operate 150 degrees Celsius, then maybe it will take some more time. But PEM electrolyzers immediately will start, almost immediately will start generating hydrogen oxygen. Alkaline may be little more time, but the solid oxide electrolyzer takes long time. I have not discussed much on solid oxide electrolyzer. It takes long time solid oxide electrolyzer because it operates about 700 to 800 degrees Celsius. It uses ceramic membrane, which is ytterstabilized zirconia. It uses anode and cathode, which is nickel, YSZ or ytterstabilized zirconia, LSM, lanthanum strontium manganate as a cathode material, and is operated about 800 degrees Celsius. So you can imagine the startup time for this will be hours. But once it's started, because it's an exothermic reaction, because you can operate both endothermic and exothermic way, solid oxide electrolyzer. So if you are operate in a thermoneutral basis, so once you started, then it will be maintaining it. So no issue at all. Okay. So that's the startup time for the different electrolyzers.
Thank you so much, sir.
Thank you. Any other question? Yes, Ananda Reddy, you can have questions you can ask. Don't feel shy. Any question, if you have anything, because if I give one-sided lecture, I have given, of course, but question answer can clarify many things, which is much better. I can, shall I read the chat? Chat box is having, okay, no question. Very good.
Sir, good evening,
Okay.
sir.
Good evening.
It is audible, sir.
Yes, audible, please.
Sir, generally we are using water for producing hydrogen energy. So instead of water, shall we use ammonia? It is possible.
Yeah, I think you are already, yeah, it is quite possible. This kind of concept is there. I have not come to that because it was a kind of that only introduction. So I can tell the hydrogen you produce now. The question is how you can transport hydrogen. So one of the way of transporting hydrogen, that hydrogen is lightest gas, you pressurized and high pressure, let's say 100 bar, 200 bar, because your volume is there, given volume, let's say cylinder. As you pressurize more and more hydrogen mass will be inside the cylinder. So you can have a hydrogen cylinder of 200 bar, 400 bar, 600, 800 bar. These cylinders are being made, and you can have more hydrogen, right? You want to store as much hydrogen in small spaces possible. This is by pressure. Another way of storing hydrogen, so pressurizing hydrogen is a lot of energy. Because suppose I'm generating hydrogen 10 bar, so I'm operating my electrolyzer at 10 bar or 10 atmosphere, and I'm storing it to about 500 bar, that you can see that I have to make pressure from 10 bar to 500 bar. And so much of compression is required. And it is very energy intensive and a lot of money. Okay, then the hydrogen cost will go up. So one of the way of storing hydrogen is to make ammonia. Because hydrogen also can be stored in the form of liquid hydrogen, and liquid hydrogen forms only at minus 180 degrees Celsius or 180 degrees Celsius. So you have to bring down the temperature to minus 180 degrees Celsius to have a liquid hydrogen, so that you have a concentrated hydrogen. So much of energy required. You have to go to 500, 600 bar to make compressed hydrogen. Instead, you make hydrogen at 5 bar or 10 bar, then you have a modified Haber-Bosch process to produce ammonia, and ammonia liquefies at about 55 minus 55 degrees Celsius. That was minus 180 degrees Celsius liquefaction of pure hydrogen, and liquefaction of ammonia is minus 55 degrees Celsius. So easy, less energy required to liquefy ammonia and store hydrogen. So people have now thought that produce hydrogen at relatively lower pressure. When a relatively lower means maybe 5, 10 bar, 20 bar. And then instead of compressing it to 200 bar or 500 bar, have a modified Haber-Bosch process, produce ammonia, liquefy ammonia, okay, and liquefy ammonia,
నేను వర్డ్ డాక్యుమెంట్ పెట్టినాను నీకు చూడు ఒకసారి
liquefy
ఎవరికి టూ ఎవరికి పెట్టాలి తెలుసుకోవాలి కదా
liquefy ammonia, okay, and then you liquefy ammonia and use liquefied ammonia as a way to transport hydrogen. So now you got ammonia, so you have to get back your hydrogen. So ammonia can be cracked to produce hydrogen, ammonia can be electrolyzed to produce hydrogen. Even some people are now trying to develop ammonia engine. Can a internal combustion engine can be produced which takes ammonia as a fuel and cylinder runs and then it gives a mobility. So ammonia has become the way to store hydrogen in the form of ammonia because it liquefies at relatively lower pressure, which is minus 50 or minus 55 degrees Celsius. Less energy is required, less cost. Then use ammonia either to crack ammonia to produce hydrogen, split ammonia to produce hydrogen in electrolysis, or use ammonia as it is for running internal combustion engine. Okay, that's possible. So ammonia cracking to produce hydrogen is possible. So shall we stop now? Any other question?
Yes, sir. I think no more questions from the participants. We will
Sir, I
stop.
have a question from co-coordinator.
Yes, sir. Please.
Yes,
So
yes,
thank you
please.
for your informative presentation. I have learned so much from you as I am also working from hydrogen and on hydrogen energy only. So I am basically working on water electrolysis to produce green hydrogen. So I have some question related, some basic fundamental in naming. So we call it as a green hydrogen because we are lowering the carbon footprint, right? But sometimes I am getting question like we are still using electricity for this water electrolysis. So can we still call it as a green hydrogen?
So you are right. You are very much, your observation is correct. So it is absolutely correct to say green hydrogen is the electricity that is required to do electrolysis coming from a photovoltaic. I also showed in my closed hydrogen loop. If it is coming from solar photovoltaic, well, that is DC output and your electrolysis also required DC, so it can be utilized. If your electricity is coming from wind power, if your electricity is coming from solar thermal power, then it can be called green hydrogen. We say green hydrogen only when everything that we are utilizing is renewable in nature or coming from solar light. Okay, so if I use photovoltaic and produce electricity, then do electrolysis, produce hydrogen from water, then it's green hydrogen. Otherwise, actually it is not. If the power is coming from grid and the grid is connected with a thermal power plant working on coal or gas, then it is obviously, it's a partially green, not fully green hydrogen. Or you can say maybe just about not qualifies as a green hydrogen. So there is a definition which is given by MNRE in their website, what would be called green hydrogen, because it's very difficult for people to get at this time photovoltaic power completely to electrolysis of water, because once you start the electrolyzer, you need to have the potential difference applied all the time. You cannot have a fluctuation and all those things. So there is a clear-cut definition given that this qualifies for green hydrogen if you are using electrolysis process, even though your electricity source is not solar photovoltaic. There is a part of electricity that is allowed from, not the entire part, a part of electricity is allowed from thermal power plant, which is given definition in MNRE, Minister of New and Renewable Energy Sources for India.
Okay, sir. Thank you. Thank you very much, sir.
Thank you. Any more question? Professor Naidu, then we can close it. You can have a closing remark and close it possibly, Professor Naidu.
Yes, sir. I think there is no questions from the participants. Dr. Bhargavi, can you give the concluding remarks? Okay, sir. Yeah, thank you very much, sir, for your valuable time. You shared a lot of information regarding that green hydrogen production, especially the electrolysis and electrolyzers, and giving the insight about that what is the green hydrogen from the fundamentals to the application point of view for our participants. I think our participants have benefited lot about from your topic, from your expert talk. So I am very much thankful to you, sir, the giving your time, your precious time during the late evening. Of course, now it is almost maybe 20 to 10. It is late evening, so still you are in office. I can I can assume that your dedication and all. So thank you very much, sir.
Thank you.
So thank you, sir. So we'll meet once again, sir. Maybe we may call some other time, sir. Okay, thank you, participants, for today's. We can end the session today. If you have any queries, let us see. Maybe you can share your queries through our WhatsApp group. Thank you, one and all. Thank you. Bye-bye. Good night. We'll see you tomorrow by 6 o'clock. So please attend the meeting before 10 minutes. 5:50 we'll meet tomorrow. Thank you.